Have you ever wondered if the reality you're experiencing right now is the only one that exists? What if, beyond the stars and galaxies we can observe, there are infinite other universes, each with its own laws of physics, its own history, and perhaps even its own version of you? This isn't science fiction. It's one of the most profound and mind-expanding ideas in modern cosmology, the concept of the multiverse. And it raises a question that has captivated scientists, philosophers, and curious minds for generations. Is our universe, with its seemingly perfect conditions for life, nothing more than a happy accident? Or is it the result of something far more intentional? Think about this for a moment. The force of gravity, the strength of electromagnetism, the mass of a proton, these aren't arbitrary numbers. They are finely tuned, breathtakingly precise constants that make life possible. If any one of them were even slightly different, atoms wouldn't form, stars wouldn't shine, and life as we know it could never have emerged. So how did we get so lucky? Some argue that in a multiverse, a vast cosmic landscape of parallel realities, it was only a matter of time before a universe like ours appeared purely by chance. Others see this fine-tuning as evidence of something deeper, something almost purposeful, as if the universe knew we were coming. This is where our journey begins. We're about to explore one of the greatest mysteries of existence, walking the line between science and philosophy, coincidence and design. Together, we'll dive into the theories that challenge our understanding of reality and question what it means to be here, in this particular universe, at this particular moment. Whether you're a science enthusiast or someone who simply loves to ponder the big questions, this exploration promises to leave you with a sense of wonder and maybe even a new perspective on your place in the cosmos. So settle in, open your mind, and let's embark on a voyage through the multiverse. So what exactly is this multiverse idea we're talking about? It starts with a simple but radical shift in perspective. For most of human history, we've looked at the cosmos and assumed that what we see is all there is, one universe with one set of rules containing everything in existence. But the multiverse theory proposes something far grander. It suggests that our universe might be just one tiny bubble in a vast cosmic foam, one page in an infinite library of realities. Each of these universes could have its own unique properties. Some might have stronger gravity, causing them to collapse instantly. Others might have no nuclear forces, so atoms never form. And a very, very few, like ours, might have just the right conditions for stars, planets, and life to emerge. The mind-bending part is that this isn't purely philosophical speculation. The concept has emerged from several different frontiers of modern physics. One major source is the theory of cosmic inflation, the idea that right after the Big Bang, space itself expanded at a staggering, exponential rate. Some physicists suggest that this inflation isn't a one-time event that created our single universe. Instead, it could be an eternal process, constantly spawning new pocket universes in an ever-growing multiverse. Each of these pockets could freeze out with a different, random set of physical laws and constants. Another path to the multiverse comes from quantum mechanics, which deals with probabilities. The famous many worlds interpretation suggests that every time a quantum event has multiple possible outcomes, the universe doesn't choose one. Instead, it splits, and every possible outcome happens in its own newly branched reality. This fundamentally challenges our entire notion of reality. It moves us from a single, definitive cosmos to a sprawling, perhaps infinite ensemble of them. It forces us to ask not just how our universe works, but why this particular one exists. Are we the result of a random cosmic lottery draw, a lucky winner in a sea of unsuccessful universes? This idea sparks an intense curiosity that bridges the gap between hard science and deep philosophy. It compels us to reconsider our place in existence, not as the center of a single creation, but as inhabitants of one possible world among a breathtaking multitude. The search for answers pushes the limits of what is knowable, blending mathematical equations with questions about meaning, purpose, and the very nature of existence itself. But to truly grasp this mind-bending concept, we need to understand that scientists aren't just talking about one single idea of a multiverse. There are several distinct theories, each emerging from a different branch of physics, painting their own incredible picture of reality's vastness. Let's start with perhaps the most well-supported model, the inflationary multiverse. This idea springs from the theory of cosmic inflation, which says that a fraction of a second after the Big Bang, the universe expanded faster than the speed of light. Now, some physicists like Alan Guth and Andre Lind propose that this inflation isn't a one-and-done event. Instead, it could be eternal. Picture a gigantic, constantly rising loaf of raisin bread. Our entire observable universe is just one single raisin within that loaf, but the dough keeps expanding forever, and new raisins, completely separate bubble universes, are constantly forming. Each of these bubbles could have its own unique physics. In one bubble, gravity might be 10 times stronger, causing it to instantly collapse into a black hole. In another, the forces that hold atoms together might be too weak, so no stars or planets ever form. Our universe just happened to be a raisin with the perfect recipe for life. Then we have the quantum multiverse, which is even stranger and comes from the bizarre world of quantum mechanics. At the tiny scale of particles, things don't follow the clear-cut rules we're used to. An electron isn't in one place, it exists in a cloud of probability with a chance of being in multiple locations at once. The standard way to explain this is that when we observe it, this probability cloud collapses and the electron picks a single location. But Hugh Everett's many worlds interpretation offers a radical alternative. It says the cloud never collapses. Instead, reality itself splits. At every moment, for every quantum decision, the universe branches. Think of it like a path constantly forking in a forest. You come to a fork and go left, but in that very same moment, another version of you goes right. Both paths are equally real. They just exist in separate, non-communicating branches of reality. In this multiverse, every possible outcome of every possible event actually happens somewhere. There's a universe where you took that different job, a universe where the dinosaurs weren't wiped out by an asteroid, and an infinite number of universes where every conceivable variation of history plays out. Finally, string theory gives us the brane multiverse. String theory attempts to unify all the forces of nature by proposing that the most fundamental things aren't point-like particles but tiny, vibrating strings. A consequence of this theory is the existence of extra dimensions beyond the three of space and one of time we experience. This is where branes come in. Brane is short for membrane, and it suggests our entire universe might be a three-dimensional brane floating within a higher dimensional space, often called the bulk. Imagine our universe as a single slice of bread floating in a vast cosmic loaf pan. There could be countless other slices, other branes floating just a millimeter away in a higher dimension we cannot perceive. These parallel universes could be right next to us, yet completely invisible. Even more incredible, the Big Bang that started our universe might have been caused by two of these branes colliding in this higher dimensional space. In this model, the laws of physics could be completely different on other branes, and a close encounter with one could send ripples through the very fabric of our own reality. With so many possible universes, some collapsing instantly, others too empty for even atoms to form, we're led to a profound and almost unsettling question. Why is our universe so hospitable to life? This brings us to the heart of the fine-tuning problem, one of the most compelling mysteries in all of science. It's the observation that the fundamental constants and forces of nature appear to be exquisitely, almost miraculously, calibrated to allow for the existence of stars, planets, and conscious beings like us. Consider gravity, the force that holds our feet to the ground and our planet in orbit around the sun. Its strength isn't arbitrary. If the gravitational constant were even slightly stronger, stars would burn through their fuel too quickly and collapse into black holes long before life could evolve. A slightly weaker gravity and stars might never ignite at all, leaving the universe a dark, cold, and sterile expanse of scattered gas. The margin for error is astonishingly small. Alter gravity by just 1 part in 10 to the 40th power. That's a 1 with 40 zeros after it, and a life-permitting universe becomes impossible. Then there's the cosmological constant, which governs the energy density of empty space and the expansion rate of the universe. This value is perhaps the most famous example of fine-tuning. If it were a little larger, the universe would have expanded so rapidly after the Big Bang that galaxies and stars could never have coalesced. Matter would have been flung apart before it could clump together. If the value were a tiny bit smaller, the universe would have collapsed back in on itself in a catastrophic big crunch almost immediately after it began. The required precision is beyond human comprehension. The constant must be fine-tuned to within 1 part in 10 to the 120th power. That number is so vast it has more zeros than there are atoms in the entire observable universe. It's a level of precision that defies belief if attributed to mere chance. We also see this delicate balance in the nuclear forces. The strong nuclear force holds the protons and neutrons together in an atom's nucleus. If this force were just a few % stronger, hydrogen atoms would fuse into helium too easily. All the hydrogen in the early universe would have been consumed, meaning no water and no long-lived stars like our Sun. If it were slightly weaker, protons and neutrons wouldn't bind together at all, so atomic nuclei, and therefore the elements essential for life would never form. The weak nuclear force, which governs radioactive decay, is also precisely set. A small change here would have drastically altered the composition of the universe after the Big Bang, leaving too few of the heavy elements like carbon and oxygen that are the building blocks of life. This isn't just about 1 or 2 lucky numbers. It's a symphony of constants, each perfectly tuned, all working in concert to create a universe that can support complexity. The charge of an electron, the mass of a proton, the ratio of the strengths of the 4 fundamental forces. Each one is a dial on a vast cosmic control board. And as far as we can tell, nearly every single dial is set to an incredibly specific value that makes life possible. The sheer number of these cosmic coincidences makes the idea that it's all a random accident feel increasingly improbable. It presents us with a genuine puzzle that sits at the intersection of physics, philosophy, and perhaps even theology, forcing us to confront the ultimate question. Why is there something rather than nothing? And why is that something so perfectly arranged for us to be here to ask the question? Facing this overwhelming evidence of fine-tuning, scientists and philosophers have proposed a fascinating and somewhat controversial way to grapple with the question of why. It's called the anthropic principle, and at its core, it's a simple statement of observational selection bias. The principle suggests that we can only observe a universe that has the right conditions for our existence. If the constants of nature were any different, we wouldn't be here to talk about it. It's a bit like a puddle marveling at how perfectly the hole in the ground it occupies is shaped to fit its water. The puddle might think the hole was designed just for it, when in reality, it's the water that conformed to the shape of the hole. In the same way, we find ourselves in a universe that fits us, but that doesn't necessarily mean it was made for us. This idea branches into 2 main forms, the weak anthropic principle and the strong anthropic principle. The weak version is the less controversial of the 2. It simply states that we must be prepared to take into account the fact that our location in the universe is necessarily privileged to the extent of being compatible with our existence as observers. In plainer terms, it reminds us that our observations are filtered by the very fact that we are alive to make them. we shouldn't be surprised to find ourselves on a planet with liquid water, a stable orbit, and a protective atmosphere. We couldn't possibly find ourselves anywhere else. This weak principle is a useful check on our assumptions, reminding us that our sample size of one universe might not be representative of a wider reality. The strong anthropic principle takes a much more speculative and profound leap. It proposes that the universe must have those properties which allow life to develop within it at some stage in its history. The word "must" is doing a lot of heavy lifting here. This version moves from a simple statement about our observational vantage point to an assertion about the necessary laws of the universe itself. Some interpretations of the strong principle lean towards a teleological or purpose-driven view, suggesting that the universe is in some sense compelled to eventually produce conscious life. This can sound almost mystical, but other interpretations try to ground it in physics, suggesting that the presence of an observer might be somehow necessary for the universe to come into being, a concept that intriguingly echoes certain ideas in quantum mechanics where observation seems to define reality. So, how do these principles attempt to resolve the fine-tuning problem without invoking a designer? The multiverse provides the most powerful framework for the anthropic principle to operate. If an infinite or near-infinite number of universes exist, each with randomly different physical constants, then it is a statistical certainty that at least one universe will have the perfect combination for life. We just happen to be in that one. The incredible unlikelihood of our universe is no longer a mystery. It's a consequence of probability across a vast landscape of realities. Our existence isn't a planned outcome. It's the result of a cosmic numbers game where we hold the winning ticket. The anthropic principle in this context is the logical answer to the question of why we see what we see. However, this explanation leaves some people deeply unsatisfied. Critics argue that using an unobservable multiverse to explain the features of our one observable universe is a form of philosophical retreat. It answers a profound mystery by invoking an even bigger one. It can feel like explaining a magician's trick by saying there are an infinite number of magicians, and we just happen to see the one show where the trick worked. Furthermore, the strong anthropic principle, with its hint of purpose or necessity, raises its own set of questions. If the universe must produce life, what does that "must" mean? Does it imply a deeper law of nature we haven't discovered, or something else entirely? The anthropic principle doesn't so much solve the puzzle of fine-tuning as it reframes it, shifting the debate from physics and cosmology toward the nature of explanation and reality itself. The sheer number of these perfectly set dials on the cosmic control board is what makes the argument for fine-tuning so powerful. Let's look at a few of the most staggering examples, starting with the most mysterious force in the cosmos, dark energy. This is the enigmatic energy infusing empty space itself, causing the universe's expansion to accelerate. Its measured value is astoundingly small. If you were to compare the theoretical predicted strength of dark energy to the strength we actually observe, the observed value is about 120 orders of magnitude smaller. That's a decimal point followed by 119 zeros and then a 1. It is by far the worst prediction in the entire history of physics. Why is this tiny number so critical? Because dark energy is the ultimate balancing act between expansion and collapse. If this value were even slightly larger by a factor of just 10, the accelerated expansion of the universe would have begun much earlier, tearing apart galaxies before they could even form. There would be no stars, no planets, no ingredients for life. If it were slightly smaller, or better yet, negative, the gravitational pull of matter would have won out long ago, causing the entire universe to recollapse into a big crunch in a fraction of its current age. The window for a life-permitting universe is unbelievably narrow, and somehow our universe landed right in the sweet spot. Then we have the initial conditions of the Big Bang itself. The universe didn't just explode into being, it was born with a specific and incredibly smooth set of properties. One of the most precise is the initial density of the universe. For the universe to have lasted for billions of years and allowed for structure to form, this density had to be exquisitely fine-tuned to a value known as the critical density. The difference between the actual density and this critical value at 1 second after the Big Bang had to be less than 1 part in a million trillion. That's a level of precision equivalent to throwing a dart from one side of the observable universe and hitting a bull's-eye just 1 millimeter wide on the other side. Any deviation and the universe would have either flown apart too rapidly or collapsed back on itself almost instantly. This incredible smoothness or flatness is one of the greatest mysteries of cosmology. It seems as if the universe was set up with impossibly perfect initial conditions. Another monumental coincidence is the matter-antimatter asymmetry. According to our best theories of particle physics, the Big Bang should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other in a flash of pure energy. If perfect symmetry had been maintained, every particle of matter would have found its antimatter counterpart, and the entire universe would have annihilated itself into a sea of radiation, leaving behind absolutely nothing, no atoms, no chemistry, no us. But that's not what happened. For every billion pairs of matter and antimatter particles that annihilated in the early universe, a single matter particle was left over. That 1 in a billion imbalance is the reason anything made of atoms exists at all. Every star, every planet, and every person is made from that tiny, inexplicable surplus of matter. We are literally the leftovers from a near-total annihilation. The profound question is, what physical law caused this tiny but universe-making violation of symmetry? We simply don't know. Each of these examples represents a razor's edge upon which our entire existence balances. They are not minor curiosities, they are fundamental prerequisites for a cosmos that can harbor complexity and consciousness. The odds against all of these conditions aligning by pure chance in a single universe are so astronomically vast that they push the boundaries of rational belief, forcing us to consider that we are either the beneficiaries of unimaginable luck or witnesses to a reality with a deeper, more profound architecture. Faced with these unimaginable odds, the multiverse theory emerges as a powerful and elegant solution to the fine-tuning problem. It reframes our incredible luck not as a miracle, but as an inevitable statistical outcome. If an infinite, or at least an incomprehensibly vast number of universes exist, each with its own random set of physical constants, then it becomes a mathematical certainty that at least one universe will, by pure chance, have the perfect combination for life. We are not witnessing a 1 in a trillion cosmic accident. We are simply inhabitants of the one universe that worked. All the other universes, the ones with gravity too strong or nuclear forces too weak, are empty, lifeless, or perhaps even stillborn cosmic ghost towns where no one is home to wonder why things are the way they are. This idea holds a profound appeal for many scientists because it offers a naturalistic explanation that stays firmly within the realm of physical law, avoiding any need to invoke a designer or a purpose. It applies a principle well known in probability. If you have enough lottery tickets, someone is bound to hit the jackpot. In this cosmic lottery, we are that winning ticket. The theory doesn't make our existence any less special, but it does make it less mystifying from a scientific standpoint. The breathtaking precision of the constants is no longer a puzzle to be solved, but a selection effect to be understood. We are here because we couldn't possibly observe a universe that couldn't support us. This perspective is deeply grounded in the scientific method's preference for testable, albeit challenging, hypotheses over untestable ones. While we cannot currently travel to other universes to confirm their existence, the multiverse theory is not pure speculation divorced from physics. It emerges naturally from our most ambitious attempts to understand the cosmos, like inflationary cosmology and string theory. For the scientists developing these models, the multiverse isn't a convenient philosophical add-on. It's a prediction that falls out of the mathematics. The appeal lies in its explanatory power. It takes a series of profound why questions and provides a coherent framework to answer them, all while pushing our understanding of reality to its absolute limits. It represents science's boldest attempt to look beyond the horizon of our single observable universe and ask what else might be out there in the grander scheme of existence. Yet for all its elegance and explanatory power, the multiverse theory is not without its fierce and compelling critics. One of the most significant charges leveled against it is that it fails a fundamental test of science, falsifiability. The core principle of the scientific method, famously emphasized by philosopher Karl Popper, is that a theory must make predictions that could potentially be proven wrong. If a concept cannot be tested, measured, or observed in any way, it risks drifting out of the realm of science and into the domain of metaphysics or even pure speculation. How do we test for the existence of other universes that, by their very definition, may be forever separated from our own by an impassable cosmological horizon? Critics argue that if no observation can ever contradict the multiverse hypothesis, then it isn't truly a scientific theory at all, but rather an untestable philosophical stance. A supporter might counter that we cannot see the atoms in a rock, but we accept their existence because the atomic theory that predicts them successfully explains a vast array of other testable phenomena. In the same way, they argue, the theories that predict a multiverse like inflation and string theory are themselves testable, and if those foundational theories are validated, we must take their predictions seriously, even the seemingly untestable ones. This leads to another major criticism, the charge of being a theory of anything. Skeptics like physicists Paul Steinhardt and George Ellis caution that by invoking an infinite array of universes where every possible physical law plays out, the multiverse theory can explain everything and therefore predicts nothing. If a measurement in our universe seems strangely fine-tuned, the multiverse answer is simply, well, in some universe it had to be that way. This, critics say, risks halting scientific inquiry rather than advancing it. Instead of searching for a deeper, more fundamental physical law that might explain why the cosmological constant is so small, for example, a scientist could just shrug and attribute it to random chance across the multiverse. It could become a conversation ender, an easy way to dismiss profound mysteries without truly solving them. In this view, the multiverse isn't the pinnacle of scientific exploration, but a potential dead end that appeals to a form of lazy reasoning, effectively giving up on the dream of a final, complete theory of everything for our one observable universe. The debate often boils down to a fundamental disagreement about the nature of science itself. Is science strictly about what we can observe and test directly? Or is it also about finding the most coherent and powerful explanations for what we see, even if they involve unobservable entities? Supporters of the multiverse lean toward the latter, viewing it as the most natural and parsimonious conclusion of our best physical models. To them, it seems more rational to accept a vast, unobservable multiverse than to believe our universe is a singular, impossibly lucky anomaly that hints at a designer. The skeptics, however, hold firm to a stricter definition of empirical science. They argue that we must be wary of constructing elaborate, invisible worlds solely to avoid other, potentially uncomfortable conclusions. This tension is not new. It echoes historic debates about other unseeable entities, from atoms to black holes, which were once considered purely theoretical before technology finally provided evidence for their existence. The hope for many multiverse proponents is that we are in a similar pre-confirmation phase, and that future breakthroughs in cosmology or fundamental physics might provide indirect but convincing evidence for realities beyond our own. On the other side of this cosmic debate stands a perspective that reaches back to the very beginnings of human wonder, the idea that such breathtaking order and precision could be the signature of a designer. Proponents of the intelligent design argument look at the same evidence of fine-tuning that fuels the multiverse theory and arrive at a radically different conclusion. For them, the exquisitely calibrated constants of nature are not the product of mindless, random chance across infinite realities, but rather the clear mark of intentional, purposeful planning. The universe, in this view, appears fine-tuned for life because it is fine-tuned for life by a mind of incomprehensible intelligence. This line of reasoning often begins with a simple but powerful analogy. Imagine you're walking on a beach and you come across a watch lying in the sand. You wouldn't assume that the waves and the sand, given enough time, randomly assembled its intricate gears, springs, and dials into a functioning timepiece. The watch's complexity and clear purpose immediately suggest a watchmaker. Now, scale that up to the entire cosmos. The laws of physics are far more complex and interdependent than any watch. The forces are precisely balanced, the constants are perfectly set, and the initial conditions were immaculately arranged to allow for galaxies, stars, planets, and ultimately conscious life. To many, inferring a designer for this cosmic watch seems not just reasonable, but the most direct and intuitive explanation available. It is an argument from effect to cause. We see the unmistakable effect of a designed universe, and therefore we infer an intelligent cause behind it. This perspective finds resonance with the classical concept of the teleological argument for the existence of God, an idea explored by philosophers and theologians for millennia, from Plato and Aristotle to Thomas Aquinas and William Paley. The modern fine-tuning argument provides a powerful scientific update to this ancient line of thought, swapping biological complexity for fundamental physics. It suggests that the universe possesses what some philosophers call specified complexity, a highly improbable configuration that also fulfills a specific, independent pattern, which in this case is being hospitable to life. Finding such specified complexity is in everyday experience a reliable indicator of intelligent agency. A single random letter drawn from a Scrabble bag is not complex. The entire sequence of letters in a Shakespearean sonnet is both complex and specified, pointing unmistakably to an author. Beyond intuition and analogy, design advocates often point to the sheer mathematical improbability of our universe as positive evidence. The odds of all the constants randomly aligning to allow for life are so astronomically small, often described as like winning a cosmic lottery millions of times in a row, that attributing it to blind chance can feel like a greater leap of faith than positing a designer. They argue that the multiverse theory, in its attempt to explain away this improbability, simply pushes the problem back a step. Even if an infinite number of universes exist, what designed or generated the multiverse generating mechanism itself? The laws that govern the inflationary vacuum or the quantum fields that spawn new universes would themselves need to be precisely set to allow for such prolific universe production. This, critics say, simply replaces one fine-tuning problem with another, more fundamental one. The need for an ultimate explanation remains. It is crucial to understand that the modern design argument is not necessarily a call to insert a specific religious deity into a gap in scientific knowledge. While many religious individuals find the fine-tuning argument compelling and consistent with their faith, the concept of a designer can also be framed in more philosophical, deistic, or even pantheistic terms. It could be an unknown, transcendent mind, a fundamental principle of cosmic reason, or an abstract, guiding telos or purpose woven into the fabric of reality. The core claim is simply that the appearance of design is real, and that the best explanation for the universe's life-friendly architecture is a mind-like cause rather than an undirected process. This stance positions itself as a legitimate inference to the best explanation based on the empirical data of physics itself. challenging the notion that science must always default to purely materialistic and chance-driven answers. Yet, stepping back from the scientific debate, we find ourselves facing a set of questions that physics alone may never be equipped to answer. The evidence of fine-tuning, whether explained by a multiverse or designer, forces us to confront the deepest philosophical puzzles about existence itself. What is the ultimate nature of reality? Does the universe possess an inherent purpose, or is our sense of meaning merely a fleeting byproduct of blind physical processes? These are not new questions, but modern cosmology has given them a startling new urgency and a fresh set of vocabulary. Consider first the nature of existence. The multiverse theory, if true, presents a vision of reality that is almost incomprehensibly vast and profoundly indifferent. In this view, our universe is not a special creation but a single roll of the cosmic dice. There is no why for our particular set of laws. There is only the statistical how of their random occurrence. This can lead to a philosophy of existential nihilism, where human life and consciousness are seen as insignificant accidents in a meaningless cosmic landscape. Our struggles, our art, our loves and losses, all of it is reduced to a random fluctuation in an infinite void. This perspective can feel liberating to some, freeing us from any predetermined cosmic script, but to others it can feel deeply alienating and empty. Conversely, the design hypothesis suggests a universe that is, at its core, intentional and rational. It implies that the laws of physics are not just brute facts, but are instead the product of a mind or a reasoning principle. This view often aligns with a philosophy of purpose or teleology, where the universe is oriented toward certain ends, like the emergence of life and consciousness. In this framework, our existence is not a random accident but part of a coherent narrative. This doesn't necessarily simplify things. It raises its own profound questions about the nature and motivations of a potential designer. But it does offer a universe that is, in principle, understandable because it was built by a rational intelligence, potentially making the scientific pursuit itself a form of deciphering a grand cosmic code. Perhaps the most intriguing philosophical bridge between these two views is the role of consciousness. We are not passive observers of this finely tuned universe, we are active products of it. Our very ability to measure the cosmological constant and ponder its significance is a direct result of the same laws we are studying. This loop of observation raises a fascinating possibility explored by thinkers like John Wheeler with his participatory anthropic principle. He suggested that observers are necessary to bring the universe into being, that the act of observation itself may somehow collapse quantum possibilities into the concrete reality we experience. This idea places consciousness not as a late arriving accident in an already existing cosmos, but as a fundamental feature of reality from the very beginning. It blurs the hard line between the observer and the observed, suggesting that the universe fine-tuned itself for life because life is an essential part of its own definition. Ultimately, the debate between a multiverse of chance and a universe of design forces us to choose between two very different stories about our place in the cosmos. One story tells us we are alone, the unlikely winners of a lottery no one designed. The other tells us we are home in a universe that was expecting us. Which story we find more compelling may say less about the universe itself and more about us, about our deepest hopes, our fears, and our innate desire to find meaning in the vast and silent dark. The scientific case for fine-tuning isn't built on philosophical speculation. It's grounded in hard, empirical data meticulously gathered from powerful telescopes and massive particle colliders. Cosmology offers some of the most compelling evidence, starting with the universe's critical density and expansion rate. Measurements from satellites like the Planck spacecraft have confirmed that the density parameter, known as omega, is incredibly close to 1. This means the universe is geometrically flat, a condition that required an unimaginable level of precision in the first moments after the Big Bang. If the initial expansion rate had differed by just 1 part in 10 to the 60th power, the universe would have either collapsed almost immediately or flown apart too quickly for any galaxies to form. This isn't a minor adjustment, it's like balancing a pencil on its tip for billions of years. The observed flatness is a direct measurement, a data point on a graph that screams fine-tuned. Particle physics deepens the mystery with its own set of exquisitely precise numbers. Research at facilities like the Large Hadron Collider has precisely measured the masses of fundamental particles, and these values turn out to be shockingly consequential. The mass of the quark, for instance, is vital for the formation of atomic nuclei. If it were much heavier or lighter, the element carbon, the fundamental building block of life as we know it, would be extremely rare or non-existent in the universe. Similarly, the mass of the electron is perfectly calibrated. If electrons were significantly heavier, they wouldn't form stable orbits around atomic nuclei, preventing the formation of molecules and all of chemistry. These aren't arbitrary values, they are the result of countless experiments, and they all fall within a razor-thin window that allows for complexity. Astrophysical observations further cement the argument by revealing the delicate balance of the forces that shape the cosmos. The strength of gravity relative to the force driving the expansion of the universe, dark energy, is perhaps the most famous example. Data from observing distant supernova, which won the Nobel Prize in Physics in 2011, confirmed that the cosmological constant is positive but incredibly small. The calculated value is around 120 orders of magnitude smaller than what quantum field theory predicts it should be. This isn't a small error, it's the largest discrepancy between theory and observation in all of science. Yet, this seemingly wrong value is perfect for life. A slightly larger value would have ripped the universe apart before stars formed, while a slightly smaller one would have caused a premature gravitational collapse. The evidence is written in the light of exploding stars across the universe. This convergence of data from independent fields of physics creates a powerful, multifaceted argument. The constants from cosmology, particle physics, and astrophysics aren't isolated numbers. They interlock like gears in a magnificent clock. A change in one would catastrophically disrupt the others. The research that has shaped this debate, from the discovery of the cosmic microwave background radiation to the detailed particle collisions in underground laboratories, all points toward the same astonishing conclusion. Our universe possesses a specific, highly improbable set of properties that make it hospitable to conscious life. This isn't a fringe idea but a central puzzle that working physicists grapple with, a mystery born from decades of rigorous experimentation and observation. While the multiverse and intelligent design present two powerful narratives, they are far from the only explanations on the table. A host of alternative theories seek to solve the fine-tuning puzzle by reimagining the fundamental rules of the game itself, proposing that our constants might not be as constant as we think, or that our universe's history is part of a much grander, repeating cycle. One compelling line of thought suggests that the fundamental constants might not be fixed, immutable numbers, but could instead evolve over time. Imagine if the strength of gravity or the mass of an electron were ever so slightly different in the distant past, slowly changing to settle into the values we measure today. This idea of varying constants offers a potential escape from the fine-tuning problem. If these values can change, then the perfect settings we observe might not be a prerequisite for the universe's beginning, but rather a destination it naturally evolved toward. However, this theory faces a significant hurdle, a mountain of precise observational data. Measurements of the light from incredibly distant quasars, which has been traveling to us for billions of years, show that the fine structure constant, which governs the strength of electromagnetic interactions, has not changed by more than a few parts in a million over the entire history of the cosmos. While not entirely ruling out some ultra-slow variation, this evidence strongly suggests that the dials on the cosmic control board have been locked in place for a very, very long time, making this a less likely solution for many physicists. Another fascinating category of ideas falls under the umbrella of cyclic cosmologies. These models propose that our Big Bang was not a unique, singular beginning, but merely one event in an endless series of cosmic expansions and contractions. The most famous of these is the conformal cyclic cosmology proposed by Nobel laureate Roger Penrose. In this mind-bending model, the distant heat-death future of our universe, a vast, cold, empty expanse, somehow becomes the high-energy, low-entropy Big Bang of a new universe. In this framework, the fine-tuning isn't a one-time miracle. It's the result of information or structure being passed from one eon to the next through some unknown physical process. The constants we see could be the product of a long cosmic evolution across countless cycles, gradually settling into life-permitting values. While elegant, these models are highly speculative and currently lack any direct observational evidence, though Penrose and others have searched for possible imprints of a previous eon in the cosmic microwave background. A third, and perhaps the most scientifically robust, alternative is the concept of a self-organizing or emergent universe. This perspective argues that the apparent fine-tuning is an illusion born from a deeper, more fundamental law of nature that we have yet to discover. Proponents of this view believe that the constants are not free parameters to be randomly set, but are instead the inevitable output of a single, overarching theory, a true theory of everything. In this scenario, the 20+ independent numbers in the standard model of particle physics and cosmology would be like different faces of a single, multifaceted diamond. They only appear independent because we haven't found the unifying geometry that connects them all. The quest for such a theory, often pursued through frameworks like string theory or loop quantum gravity, is the holy grail of physics. If successful, it would reveal that the universe couldn't have been any other way. The constants are what they are because the deeper mathematics of reality demands it. This would resolve the fine-tuning problem not by invoking infinite chances or designer, but by showing that there was never any choice to begin with. When we compare the plausibility of these alternatives, we are essentially weighing a balance of assumptions. The varying constants theory is constrained by robust empirical data, limiting its scope. Cyclic models are mathematically elegant but currently untestable, residing in a similar speculative space as the multiverse. The concept of a single, underlying physical law is perhaps the most appealing to a physicist's desire for elegance and parsimony, but it remains a distant dream without a concrete formulation. Each alternative challenges a different assumption. Varying constants challenge the assumption of immutability, cyclic models challenge the assumption of a singular beginning, and a theory of everything challenges the assumption of independent free parameters. None have yet dethroned the multiverse or design as the leading interpretations, but they serve as crucial reminders that the conversation is far from over, and that the human drive to find a simpler, more elegant explanation continues to push the boundaries of cosmology. While the multiverse has become a serious topic of scientific debate, its journey into our collective consciousness has been paved not by physics papers but by the power of storytelling. It's in the realm of pop culture that these mind-bending ideas truly come to life, allowing us to explore the emotional and dramatic weight of infinite possibilities in a way that equations alone never could. The most explosive recent example is without a doubt the Marvel Cinematic Universe. Their sprawling narrative has masterfully used the multiverse as both a plot device and a philosophical playground. We've seen different versions of beloved heroes like Spider-Man, some tragic and some hilarious, collide in a single reality. We've witnessed a variant of the hero Doctor Strange become a universe-destroying villain, and we've followed Loki on a journey that essentially breaks the timeline itself, leading to a cosmic authority, the Time Variance Authority, whose sole job is to prune branches of reality that deviate from a single, sacred timeline. This isn't just a gimmick, it taps into a universal curiosity about the paths not taken. What if I had made a different choice? What would I be like in another life? Marvel packages this profound question with spectacular action and humor, making it accessible and thrilling for a global audience. But long before superheroes dominated the box office, science fiction literature was plumbing the depths of these concepts with breathtaking originality. One of the most iconic and enduring explorations is Philip K. Dick's classic novel, The Man in the High Castle. This story presents a world where the Axis powers won World War II, and America is divided between Japanese and Nazi control. The genius of the narrative isn't just the alternate history itself. It's the characters' gradual discovery of artifacts from our reality, like a banned newsreel showing the Allies victorious, which suggests that their grim world is just one possibility among many. This creates a profound sense of cognitive dissonance and yearning, forcing both the characters and the reader to question the solidity of their own reality. It's a far more sobering and philosophical take than the superhero genre, using the multiverse to explore the weight of history, the nature of truth, and the fragility of freedom. Television has also become a fertile ground for these explorations, often focusing on the intimate, personal stakes of branching realities. A brilliant example is the acclaimed series The Good Place, which is fundamentally a comedy about ethics and moral philosophy. In its final season, the show introduces a metaphysical waiting room where every human who has ever lived can test thousands of different life paths to see if they become a better person. We see a character literally try on different lives, making small changes that lead to radically different outcomes. This is a powerful, relatable metaphor for the multiverse that makes an abstract concept deeply personal. It's not about universe-ending threats, it's about the quiet, everyday choices that define who we are. Similarly, the sci-fi drama Counterpart starring J. K. Simmons used a Cold War-style espionage thriller to examine how a single life can diverge. Two versions of the same man, one a low-level bureaucrat and the other a ruthless secret agent, are forced to confront each other, exploring how their identical starting points were shaped by different experiences and traumas into completely different men. The tension comes from the characters facing their own potential for both good and evil. So why does this concept hold such a powerful grip on our imagination? The resonance is multifaceted. On one level, it's the ultimate form of wish fulfillment and a salve for regret. The idea that somewhere out there, a version of you made the right choice, got the girl, averted that tragedy, or fulfilled their dream is a profoundly comforting thought. It alleviates the crushing finality of our decisions, offering a cosmic safety net for our mistakes. On a deeper level, it serves as a narrative tool to explore identity. By seeing multiple versions of a character, we are able to separate their core essence from the circumstances that shape them. What makes you you? Is it an unchangeable soul, or is it merely the sum of your experiences? These stories allow us to dissect that question in the most dramatic way possible. Perhaps most importantly, the multiverse in pop culture acts as a giant metaphor for the human condition in the modern world. We live in an age of infinite choice and parallel digital lives through social media. We constantly curate different versions of ourselves for different audiences, our professional self, our family self, our online self. We are acutely aware of the paths we didn't take, constantly comparing our reality to the highlight reels of others. The multiverse narrative externalizes this internal conflict, giving it a shape and a story we can follow. It allows us to physically see the ghost of the person we might have been and grapple with that image. By watching these stories, we aren't just being entertained, we're working through our own anxieties about choice, fate, and identity, using the grand canvas of the cosmos to better understand the universe within ourselves. This dialogue between fine-tuning and faith isn't just a modern debate. it reaches back centuries, finding a surprising harmony in the concept of natural theology. This is the idea that knowledge of God can be reached through the observation of the natural world and the use of reason, rather than solely through revelation. For many thinkers throughout history, from medieval Islamic scholars to Christian philosophers, the intricate order and design apparent in nature were themselves a form of divine testimony. They looked at the precise movements of the planets, the complexity of a living cell, or the changing of the seasons, and saw not random chance, but the fingerprints of a creator. The modern fine-tuning argument is in many ways a direct descendant of this ancient tradition, simply updating the evidence from the biological world to the fundamental constants of physics. It replaces the watch found on a beach with the unimaginably precise calibration of the cosmological constant, but the fundamental inference remains strikingly similar, that such breathtaking order points toward a mind. Different religious traditions engage with this evidence in distinct and fascinating ways. Within Christianity, many see the fine-tuned universe as powerful support for theistic belief, a scientific validation of the opening lines of the Book of John, "In the beginning was the Word." They argue that a universe governed by rational, discoverable laws is exactly what one would expect if it were created by a rational God. Pope Francis himself has stated that the Big Bang theory and evolution are not incompatible with Catholic doctrine, describing God as not a magician but a creator who brought everything to life. This view allows scientific discovery to illuminate the how of creation, while faith addresses the ultimate why. In Islam, the Quran repeatedly urges believers to reflect upon the natural world as a sign of Allah's power and wisdom. The precise balance and measure evident in the cosmos, known as mizan, is a central theme. For many Muslim scientists and philosophers, the fine-tuning data is a modern empirical confirmation of this divine equilibrium, a tangible manifestation of the perfect order Allah has established in all things. Eastern religions often offer a different but no less compelling perspective. In Hinduism, the universe is frequently seen as cyclical and endlessly generative, with periods of creation, preservation, and dissolution. The concept of a finely tuned single universe can be absorbed into this grander cyclical view, where the constants might be reset with each new cycle by a divine principle or Brahman. The intricate laws of physics could be seen as the manifestation of a deeper cosmic order or Rita. Buddhist philosophy, with its emphasis on interdependence and conditioned arising, might interpret the fine-tuning not as evidence for a single creator God, but as an illustration of the profound and seamless web of cause and condition that allows for reality and conscious life within it to manifest at all. The fact that consciousness exists to observe the universe is not a puzzle to be solved, but a fundamental part of the interdependent whole. This brings us to the core question: can science and spirituality truly coexist in explaining our origins, or are they fundamentally at odds? The conflict narrative, often dubbed the war between science and religion, is a powerful one in popular culture, but many scholars and scientists argue it is a vast oversimplification. A more nuanced view is that science and religion operate in different, complementary realms of human understanding. Science is our most powerful tool for investigating the mechanics of the universe, the physical processes, the mathematical relationships, the how. It deals with objective, testable, and measurable phenomena. Spirituality, on the other hand, traditionally deals with questions of meaning, purpose, value, and ultimate cause, the why. From this perspective, asking a particle accelerator to prove the existence of God is like asking a telescope to tell you the meaning of love. You're using the wrong tool for the job. Many scientists, who are also people of deep faith, see no contradiction in this complementary approach. They can wholeheartedly accept the scientific narrative of the Big Bang and cosmic evolution, while simultaneously maintaining a belief that this magnificent, rational, and life-giving process is itself the expression of a divine intention. The laws of physics are not a replacement for God, but the language through which God creates. This framework allows for a rich dialogue where scientific discoveries can deepen spiritual awe, and spiritual questions can inspire new scientific curiosity about the nature of reality. The evidence of fine-tuning doesn't force a single conclusion, but rather opens a space for a profound and personal conversation about what we believe, what we know, and how we find our place in a universe that seems strangely and wonderfully made for our existence. If the fundamental principles of our reality are not fixed laws but simply the local bylaws of our particular cosmic neighborhood, then our entire approach to technology could be fundamentally rewritten. The implications reach far beyond theoretical physics, potentially unlocking capabilities that today seem like pure magic. Let's start with the most tangible frontier, quantum computing. Right now, we struggle to maintain coherence in our fragile qubits, fighting against decoherence as our quantum states collapse. But if the many worlds interpretation is correct, a quantum computer isn't just performing calculations in one reality. It's effectively harnessing the computational power of an infinite number of parallel universes. Each possible outcome of a quantum operation isn't a probability, it's a result being calculated in a different branch of the multiverse. A fully realized quantum computer, in this view, would be less a machine and more a portal, a device that can access and synthesize answers from a near infinite number of versions of itself. The processing power wouldn't be merely exponential. It would be limitless, capable of solving problems like climate modeling or disease simulation in an instant by canvassing every possible solution across the multiverse. This concept could extend into the very fabric of energy generation. Imagine if we could tap into the fundamental fine-tuning itself. Scientists at the Large Hadron Collider are already searching for extra dimensions predicted by string theory. If they exist, and if our universe is a brane floating in a higher dimensional bulk, what prevents energy from leaking between these dimensions? A futuristic technology might not just generate energy, but siphon it from the vast, untapped reservoirs of these parallel realms. We could be like islands in an archipelago, learning to draw power from the ocean currents flowing between us. Or consider the cosmological constant, that inexplicably tiny amount of dark energy causing our universe to expand. If we could ever understand why its value is so perfectly set, we might learn to manipulate the fabric of spacetime itself, controlling the expansion of space to create unimaginable energy sources or even engines for interstellar travel. The most profound application, however, might lie in the field of communication. If other universes exist, could we ever send a signal across the void? The laws of physics in our universe prevent any information from traveling faster than light, creating an insurmountable barrier within our cosmic horizon. But what if information doesn't have to travel through space? Quantum entanglement already presents us with spooky action at a distance, where particles instantaneously influence each other regardless of separation. Some theorists have speculated that this entanglement might not be limited to our universe, that particles could be entangled across the multiverse itself. A technology based on this principle wouldn't be a radio, it would be a reality link, a device that allows for communication between different versions of Earth. The data stream wouldn't be a simple message, but an entire probability cloud of information, a glimpse into how history unfolded differently elsewhere. This wouldn't just revolutionize technology, it would transform every aspect of human civilization. We could consult with versions of ourselves who made different choices, learning from their triumphs and their failures. A global crisis on our Earth could be averted by receiving the solution from an Earth that already solved it. We could access the combined artistic and scientific knowledge of infinite civilizations, creating a cultural and intellectual exchange on a scale beyond comprehension. Of course, such power carries unimaginable risks. Opening a channel to a universe with hostile intentions or a dangerously different physics could be catastrophic. The ethical dilemmas would be profound. Do we have a right to interact with these other worlds? Would it be interference or collaboration? The development of such technologies would force us to grow up not just as a species, but as a reality, learning to navigate an infinitely more complex and interconnected cosmos than we ever dreamed possible. These mind-bending possibilities don't just challenge our understanding of physics, they force us to confront profound ethical dilemmas that could reshape the very foundations of human morality. If infinite versions of ourselves exist across the multiverse, what responsibility do we bear toward these other beings? The moment we accept that countless conscious beings might be experiencing joy and suffering in parallel realities, we face an ethical landscape of staggering complexity. Philosophers call this the problem of moral proximity. We generally feel stronger obligations to people closer to us, family over strangers, humans over animals, earthlings over hypothetical aliens. But where do other universe versions of ourselves fall on this spectrum? If a technology allowed us to communicate with or even affect these other realities, would we have a moral duty to prevent suffering in universes we could potentially influence? This isn't abstract speculation. It's a fundamental challenge to our ethical frameworks that were developed for a single, isolated reality. Consider the concept of personal identity across these infinite branches. The you in another universe might share your memories up to a certain point, then diverge based on a different choice. Are they truly you or a separate person? This question has tangible consequences for how we value life. If a disaster wiped out an entire Earth in another universe, would it be a tragedy equivalent to our Earth's destruction, or somehow less significant because it's elsewhere? This forces us to ask whether consciousness itself has intrinsic value regardless of its location in the multiverse. The answers could redefine everything from our concept of human rights to our understanding of what it means to be an individual. If all possible versions of us exist somewhere, does that diminish the significance of any single life, or does it amplify the preciousness of conscious experience everywhere? The potential for interaction creates even thornier problems. Imagine discovering a universe where your alternate self made a choice that led to tremendous suffering. Would you have an obligation to help them? What if helping them required sacrificing resources in your own universe? This scenario becomes especially troubling when we consider power dynamics between universes. A technologically advanced civilization in one reality might be tempted to intervene in less developed ones, repeating all the ethical failures of colonialism but on a multiversal scale. They might justify it as helping or guiding these other worlds, but without careful ethical guardrails, such interventions could easily become a form of cosmic imperialism. The prime directive from Star Trek would need to be reimagined for an infinitely more complex reality. These questions extend beyond hypothetical scenarios to how we live our lives right now. The knowledge that every road not taken is being traveled somewhere else could either liberate us from regret or paralyze us with a sense of meaninglessness. If every possible outcome exists, does our specific choices here and now matter less? Some philosophers argue the opposite, that the multiverse concept makes our conscious experience in this particular branch all the more precious. We are living the only version of reality that we will ever directly experience, which means our actions, relationships, and moral decisions retain their full weight and significance. The existence of other possibilities doesn't diminish the reality of our lived experience. It highlights its uniqueness within the grand tapestry of existence. Ultimately, multiverse theories don't provide easy answers to these ethical questions. They magnify them to cosmic proportions. They challenge us to expand our moral imagination beyond the confines of a single universe and consider our place in a potentially infinite ethical community. Whether we ever make contact with other realities or not, seriously contemplating these ideas pushes us toward a more humble, compassionate, and expansive view of what it means to be human in a reality far stranger and more interconnected than we ever dreamed. So where do we go from here? How do we move these mind-bending theories out of the realm of pure philosophy and into the rigorous world of testable science? The quest is already underway, with physicists designing ingenious experiments to search for fingerprints of other universes, or to determine if the fine-tuning we observe is the only possible outcome of a deeper law. This isn't about building a starship to visit another reality. It's about looking for faint, subtle clues hidden in the data we can collect right here in our own cosmos. One of the most promising frontiers is the continued study of the cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky. This ancient light is a snapshot of the infant universe, and it may contain the scars of cosmic collisions. If our universe is indeed one bubble in a frothing multiverse, it's possible that it gently bumped into another bubble in the distant past. Such a collision would have sent ripples through the fabric of space-time, potentially leaving a distinct, asymmetric pattern in the cosmic microwave background. Researchers are meticulously analyzing data from telescopes like the Planck satellite, searching for any unusual patterns in the polarization or temperature of this radiation that could be the telltale bruise from a run-in with a neighboring universe. While no definitive evidence has been found yet, the search continues, with next-generation observatories promising even more detailed maps of this primordial light. Meanwhile, deep underground in massive particle accelerators like the Large Hadron Collider, scientists are pushing matter to extreme energies, recreating the conditions of the early universe. One key goal is to find evidence for supersymmetry, a cornerstone of many string theory models. Supersymmetry predicts that every known particle has a heavier, superpartner particle. The discovery of these particles would provide crucial support for string theory, which is a primary pathway to the multiverse idea. Furthermore, these high-energy collisions might produce microscopic black holes or reveal evidence of extraspatial dimensions. If we could detect a particle that seems to disappear into a higher dimension or create a tiny gravitational anomaly, it would be revolutionary, offering the first experimental hint that our three-dimensional world is just a slice of a much larger, higher-dimensional reality, a core concept of the brane multiverse. Theoretical work is also advancing at a rapid pace. String theorists and cosmologists are refining their models, looking for ways to make concrete predictions that can be tested. Some are exploring whether the specific type of inflationary field that spawned our universe would leave a unique signature on the distribution of galaxies we see today. Others are investigating the quantum nature of gravity, seeking to understand how information might be preserved or transmitted. A major focus is on the holographic principle, the radical idea that all the information contained in a volume of space can be encoded on its boundary. This line of inquiry could reveal a fundamental limit to the number of possible universe configurations, potentially showing that life-permitting settings are not as improbable as they seem. Each of these avenues represents a different path toward the same goal, transforming the multiverse from a fascinating mathematical possibility into a robust scientific framework with observational consequences. The future of this research is a collaborative, global effort combining the immense power of particle colliders, the sharp eyes of space telescopes, and the brilliant minds of theorists. It's a long-term endeavor requiring patience and precision, as the clues we seek are incredibly faint and subtle. But the potential payoff is the greatest imaginable, a complete rewriting of our cosmic story, and a definitive answer to the ancient question of whether we are alone in existence or one thread in an infinite tapestry of realities. So where does all of this leave you personally right now, as you think about your own life and this vast cosmos? After journeying through the science of the multiverse and the philosophy of fine-tuning, it's only natural to turn that lens inward. We all carry with us a personal cosmology, a set of assumptions often unspoken about how the universe works and whether there's an underlying meaning to it all. Maybe you've never put it into words, but you feel it. It's the quiet wonder you get looking up at a starry night sky, or the pang of unease when you consider the sheer scale of emptiness between galaxies. This isn't just about physics, it's about the story you tell yourself to make sense of your place in existence. Take a moment to think about a major crossroads in your own life. Perhaps it was choosing a college, ending a relationship, or moving to a new city. Remember the weight of that decision, the feeling that you were standing at a fork in the road, consciously shaping your future. Now consider the many worlds interpretation of quantum mechanics. It suggests that at that very moment of choice, the universe didn't select a single path. Instead, it split. In another reality, a version of you made the other choice. That person's life unfolded differently, with its own unique joys and sorrows. Does that thought bring you comfort, making regret feel lighter because somewhere that other possibility is being lived out? Or does it make your actual life feel somehow less significant, as if your specific choices are just one roll of the dice in an infinite casino? There's no right answer here, only what resonates with your own heart. Perhaps you find the idea of a multiverse of pure chance to be a lonely one. If our universe is just a random accident in an infinite sea of failed realities, then our struggles, our art, our love for each other, are these just fleeting, meaningless fluctuations? Or does the opposite become true? Does the incredible unlikelihood of our existence against such impossible odds make this one life we know infinitely more precious? It's like finding a single, perfectly formed rose growing in a vast, barren desert. Its rarity doesn't diminish its beauty, it magnifies it. Every moment of connection, every act of creativity, becomes a quiet rebellion against the cosmic silence, a way of saying that in this one universe at least our lives matter. On the other hand, maybe the notion of a designer or a deeper purpose feels more true to your experience of the world. Have you ever looked at the intricate pattern of a snowflake, the perfect spiral of a nautilus shell, or the astonishing complexity of the human eye, and felt a sense of awe that transcends scientific explanation? That feeling that there is an order and a beauty to reality that hints at something more is a powerful and deeply human response. It doesn't require you to reject science. Instead, it can be about seeing the equations not as cold, hard facts, but as the elegant brushstrokes of a masterpiece. In this view, your desire to find meaning isn't an illusion. It's a clue, a feature of the universe that points toward its source. Ultimately, you're leaning toward coincidence, design, or a third, more nuanced option is shaped by your entire life's journey. It's woven from your experiences, your values, and the things you hold dear. The beauty of this moment is that science hasn't closed the book on this question. It has simply given us a new, more profound vocabulary with which to have the ancient conversation. So give yourself permission to sit with the mystery, to not have a final answer. The universe has spent billions of years evolving into a state where it can finally begin to understand itself through you. However you make sense of it all, your curiosity and your wonder are not insignificant. They are the latest, most beautiful expressions of a cosmos becoming conscious. This vibrant debate has drawn in some of the brightest minds across disparate fields, each bringing their unique perspective to the table. On one side, you have towering figures in physics like the late Stephen Hawking, who saw the multiverse as the most elegant and naturalistic solution to the fine-tuning puzzle. In his final book, he argued that the apparent miracle of our universe's constants is simply a selection effect. With a vast or infinite number of universes, he wrote, it's inevitable that one would have the right conditions, and we are by definition in it. He famously stated that this makes the quest for a single theory of everything for our universe obsolete, as the multiverse concept provides the answer. This view is passionately shared by many prominent cosmologists, including Max Tegmark, who categorizes different types of multiverses and argues they are direct predictions of our current best theories, not mere philosophical whimsy. Arrayed against this view are equally brilliant and respected scientists who caution that this is a step too far. Renowned physicist and Nobel laureate Roger Penrose, for instance, finds the multiverse explanation deeply unsatisfying. He argues that the probability of a universe like ours arising by random chance, even in an infinite multiverse, is so astronomically small as to be effectively zero, comparing it to the impossibility of the universe's low entropy start. For Penrose, this points not to a multiverse, but to the need for a deeper, more profound theory that we have yet to discover, one that would explain why the universe must be the way it is. He is joined in his skepticism by Paul Steinhardt, a pioneering architect of inflationary theory who has now become one of its most vocal critics. Steinhardt argues that the multiverse is a theory of anything because it can explain everything and thus predicts nothing, making it effectively untestable and therefore outside the bounds of science. The philosophical community is just as divided, wrestling with the logical implications of these cosmic ideas. Proponents of the multiverse, like philosopher David Lewis, argued for a doctrine called modal realism, the idea that all possible worlds are just as real as our own. This provides a sturdy philosophical foundation for the many worlds interpretation of quantum mechanics, suggesting that every possible outcome is actualized somewhere. On the other side, philosophers of science like Karl Popper would likely argue that the multiverse fails his crucial criterion of falsifiability. If we can never observe, test, or interact with these other universes, can the idea truly be considered scientific? This camp worries that accepting the multiverse could represent a retreat from empirical science back into metaphysical speculation, akin to the arguments for an unseen designer. Theologians and religious scholars engage with this evidence from yet another angle. Some, like physicist and Anglican priest John Polkinghorne, see the fine-tuning as deeply compatible with theistic belief. He argues that the rational intelligibility of the universe expressed through these precise mathematical laws points toward a divine mind. For him, the multiverse doesn't solve the problem. It just pushes it back a step, as one must then explain what fine-tuned the laws of the multiverse-generating mechanism itself. This is known as the "who tuned the multiverse" objection. Other theologians propose a fascinating synthesis, suggesting that a creator might indeed have employed a multiverse as the mechanism of creation. In this view, God is not a cosmic magician who fine-tuned a single universe, but a prolific author writing an infinite library of stories, each with its own internal consistency and beauty. Our universe is simply the one we inhabit. This collision of worldviews, scientific, philosophical, and theological, ensures the debate remains one of the most dynamic and unresolved in modern thought. It's a conversation that is far from over, with new data and new arguments continually reshaping the landscape. The very fact that such a fundamental question about reality remains open is a testament not to a failure of science, but to its vibrant and exploratory spirit, constantly pushing at the very boundaries of what we can know. If the existence of countless other realities feels like an abstract scientific concept, wait until we consider the role of the one thing experiencing all of this, consciousness itself. This is where the conversation moves from the physics of the external cosmos to the profound mystery of our internal experience, and the two might be far more deeply connected than we ever imagined. Some of the most intriguing ideas at this frontier suggest that consciousness isn't a late-arriving accident in a pre-existing universe, but may instead be a fundamental feature of reality, as basic as space and time. This perspective, known as panpsychism, proposes that some form of mind or experience is present in all matter, from a human being to an electron. In a multiverse context, this becomes staggering. It implies that every single one of those infinite universes, no matter how bizarre its physics, might be teeming with some form of inner experience. A universe that collapsed instantly after its Big Bang might have had a fleeting moment of primitive consciousness. A reality made of nothing but swirling radiation could possess a form of awareness utterly alien and incomprehensible to us. This view radically re-enchants the cosmos, suggesting that existence is not a cold, mechanical process, but is instead alive with experience at every level and in every conceivable reality. This leads us directly to one of the most mind-bending interpretations of quantum mechanics and its relationship to the observer. You've likely heard of the famous double-slit experiment, where particles seem to behave as waves of possibility until they are observed or measured, at which point they collapse into a definite particle. The question that has haunted physicists for a century is, what exactly constitutes an observation? Does it require a conscious human being or simply a mechanical detector? The most straightforward interpretation of the math suggests that the wave of probability only collapses upon interaction with a conscious observer. This places consciousness not as a passive byproduct of the brain, but as an active participant in shaping reality. Now extend this idea across the multiverse. In the many worlds view, there is no collapse. Every possibility is realized. But this raises a fascinating question. Does a branching universe only become concretely real when a conscious being within it observes it? Or is the sheer existence of a conscious observer the very thing that causes a branch to solidify from a mere possibility into a full-fledged reality? This idea blurs the line between the physical world and the mind to an almost unbelievable degree, suggesting that we are not just living in the multiverse, but that we are essential actors in its ongoing creation. These concepts force us to confront the so-called hard problem of consciousness articulated by philosopher David Chalmers. The easy problems involve understanding the mechanics of the brain, how we process information, focus attention, or discriminate between stimuli. The hard problem is explaining why and how any of this physical processing should give rise to a subjective, inner experience at all. Why does the firing of neurons in a particular pattern feel like the color red, or the taste of chocolate, or the feeling of love? Materialist science has struggled to answer this. The multiverse framework offers a potential, albeit speculative, solution. If consciousness is fundamental, then the hard problem flips. It's not about how matter creates consciousness, it's about how consciousness, as a basic property of reality, interacts with and shapes matter. Our brains, then, might not be generators of consciousness, but rather receivers or filters for a consciousness that is already everywhere, tapping into this fundamental property in a way that allows for our rich human experience. In an infinite multiverse, there would be an infinite variety of ways for this fundamental consciousness to be received and expressed. Ultimately, this fusion of multiverse theory and consciousness studies brings us full circle to the fine-tuning problem in a deeply personal way. The constants of the universe are not just fine-tuned for the existence of generic life. They are fine-tuned for the emergence of conscious observers capable of wondering about their own existence. This is known as the participatory anthropic principle, a concept championed by physicist John Archibald Wheeler. He suggested that we live in a participatory universe where observers are necessary to bring the universe into being. In his famous phrase, it's as if the universe is a giant feedback loop where it gives rise to observers, and those observers, through the act of observation, give tangible reality back to the universe. In a multiverse landscape, this means our universe isn't just one that allows for us. It's one that, in some profound sense, requires us to complete it. The lines between the scientist and the experiment, the observer and the observed, the mind and the cosmos dissolve into a single, self-referential whole. It presents a vision of reality where the quest to understand the universe is not a separate activity from the universe understanding itself through us. This intricate cosmic dance of finely tuned constants might feel a billion light-years away from your morning coffee, but the truth is, you experience a miniature version of this delicate balance every single day. Think about the last time you got into your car. You didn't marvel at the fact that the engine turned over, but that simple event relies on a precise series of coincidences. The battery had just enough charge, the spark plugs fired at the exact millisecond, the fuel pump delivered the perfect mixture of gas and air. If any one of those finely tuned systems had been even slightly off, you'd be stranded in your driveway. Your car is a tiny, man-made universe with its own set of physical laws that must be perfectly aligned for it to function. We don't call it a miracle when it starts, we call it engineering. But the principle is the same, a complex system where all the parts work in concert to produce a specific, desired outcome. We see this pattern of fortunate alignment everywhere we look, often in ways we simply take for granted. Consider your own existence. The odds of you being you, of that specific sperm cell fertilizing that specific egg cell at that exact moment in time, are astronomically small. The chain of events that had to occur for your parents to meet, for their parents to meet, stretching back through generations, is a tapestry of coincidences so intricate it defies calculation. And yet here you are. We might call it luck or fate, but it mirrors the cosmic question on a personal scale. Is the story of your life just a series of happy accidents, a random walk through an infinite garden of forking paths? Or does it feel, in some way, like a narrative with a certain direction, where certain events seem to conspire to bring you to where you are now? This isn't to suggest a predetermined destiny, but rather to highlight how we, as humans, are wired to find patterns and meaning in the chaos, both in our own lives and in the cosmos. Even the technology you're using right now to watch this video is a product of this same kind of fine-tuning, just in the realm of human innovation. The internet, your smartphone, the global network of servers, they all function because thousands of engineers independently worked on systems that ultimately had to be perfectly compatible. The protocols that allow data to flow seamlessly around the world are a masterpiece of coordination, a digital universe with its own exquisitely tuned constants. If one line of code were out of place, the entire system could fail. We achieved this not by chance, but through immense collective intelligence and intention. This gives us a powerful analogy for the cosmic fine-tuning argument. When we encounter a system of incredible complexity and precision that works flawlessly, be it a smartphone, a super collider, or a symphony, we immediately infer a designing intelligence behind it. It is our most natural, intuitive response. So when we look at a universe whose laws are millions of times more precise and complex than any human invention, is it so unreasonable to have that same intuitive response? To wonder if the universe itself shows the hallmarks of a grander form of engineering. These everyday parallels don't prove anything about the cosmos, but they do something perhaps more important. They make an abstract, dizzying scientific concept feel tangible and relatable. They build a bridge from the quark to the question of your purpose. They allow us to hold two ideas in our minds at once: the breathtaking, statistical unlikelihood of our reality, and the profound, personal sense that our journey through it matters. Whether you see the universe as a masterpiece of chance or a masterpiece of design, recognizing the fine-tuning all around us, from the engine in your car to the blood pumping through your heart, invites a deeper appreciation for the fragile, miraculous balance that makes our everyday experience possible. It turns the universe from a cold, distant void into a place that feels, in some strange and wonderful way, like home. These profound questions about the nature of reality are not confined to physics labs and philosophy seminars. They ripple outward, shaping our culture, our educational systems, and even the policies that guide our future. The way a society grapples with concepts as vast as the multiverse and fine-tuning reveals its deepest values and its vision for humanity's role in the cosmos. At the heart of this cultural impact is a fundamental tension between two powerful narratives, one of boundless possibility and one of singular, precious significance. In the realm of popular culture, we see this tension play out constantly. The explosion of multiverse stories in films, television, and literature isn't just a creative trend. It's a collective working through of these ideas on a massive scale. When audiences worldwide flock to see stories about infinite versions of Spider-Man, they are not just being entertained. They are participating in a modern myth-making process that explores a crucial question. If every choice creates a new reality, does that make our choices more meaningful or utterly meaningless? These narratives provide a safe space to experiment with the emotional consequences of these theories. They can foster an incredible sense of curiosity and open-mindedness, encouraging people to think beyond the limits of their own experience and consider perspectives they had never imagined. A teenager watching a show like Everything Everywhere All at Once might be inspired to see their own struggles and family relationships in a new, more compassionate light, understanding that different circumstances could have led to vastly different outcomes. This narrative framework can be a powerful tool for building empathy and reducing rigid black and white thinking. However, this same cultural force can also veer into a sense of nihilistic overwhelm. If every possible outcome is true somewhere, then what is the point of striving, suffering, or caring about the outcome in this reality? This is a potential cultural shadow of the multiverse idea. It can be used to rationalize a detachment from the urgent problems of our world, fostering a mentality that if things go wrong here, it doesn't ultimately matter because a version of us somewhere else got it right. The challenge for educators and communicators is to steer the conversation away from this nihilistic ditch and toward a concept of profound responsibility. The perspective isn't that our actions don't matter, but that they matter here in the one reality we directly influence. This makes our local world, our community, and our planet not less important, but immeasurably more so, as it is the only branch we have the agency to shape for the better. This cultural conversation directly influences education, particularly in how we teach science. A curriculum that introduces the multiverse as a serious, albeit speculative, consequence of our best theories of quantum mechanics and cosmology can be incredibly empowering. It teaches students that science is not a static set of facts in a textbook, but a living, breathing, and wonderfully bizarre process of discovery. It shows them that the biggest questions are still wide open, waiting for their generation to help answer them. This approach can ignite a passion for physics and philosophy in students who might otherwise find traditional science dry and disconnected from the big, why questions they care about. It encourages critical thinking, forcing them to weigh evidence, understand the limits of knowledge, and grapple with the distinction between testable science and philosophical interpretation. Conversely, introducing the fine-tuning argument in an educational setting must be handled with nuance and care. It presents a golden opportunity to teach the history of ideas, showing how the same empirical data, the precise values of the cosmological constant and the masses of subatomic particles can be interpreted through different worldviews. A well-designed lesson wouldn't advocate for one conclusion over the other, but would instead guide students through the evidence and the logical structure of both the multiverse and design arguments. This cultivates intellectual humility and philosophical literacy, skills that are desperately needed in a world often divided by dogmatic thinking. It teaches young people that it is possible to engage respectfully with profound disagreements, not as a battle to be won, but as a shared exploration of a magnificent mystery. The influence of these ideas even extends, often indirectly, into the realm of policy and our long-term planning as a species. Our vision for the future is inevitably shaped by our estimate of humanity's cosmic significance. If one subscribes to the view that we are a fleeting accident in a lonely universe, the primary political and ethical imperative might narrow to one of simple survival and maximizing well-being within our brief window of existence. However, if one entertains the possibility that we are participants in a vast, fine-tuned, and perhaps even conscious cosmos, a deeper sense of purpose can emerge. This perspective can fuel ambitious, long-term projects aimed not just at survival, but at stewardship and understanding. It can provide the philosophical underpinning for endeavors like protecting our planetary environment, not merely as an act of self-preservation, but as a duty of care for a rare and precious oasis of life. It can justify the immense investment in fundamental scientific research, like building ever larger particle colliders or space telescopes, driven by the belief that uncovering the architecture of reality is one of the highest callings of a conscious species. Ultimately, whether these concepts lead to curiosity or nihilism, to a sense of wonder or a sense of insignificance, depends less on the theories themselves and more on the stories we choose to tell about them. A society that frames the multiverse as a cosmic carnival of distraction risks fostering apathy, but a society that frames it as a testament to the incredible potential of existence can inspire a new renaissance of creativity and exploration. Similarly, a culture that uses fine-tuning to close down conversation and insist on a single, dogmatic answer stifles curiosity, but one that presents it as an open invitation to awe, a mystery that connects the quantum realm to the grandest scales of the cosmos, can unite people across disciplines and beliefs in a shared sense of wonder. The greatest impact of these ideas may be their power to remind us that we are part of a story that is still being written, and that the next chapter depends on the choices we make right here, right now, in this one precious reality. So as we stand here at the edge of this cosmic mystery, looking out at the infinite possibilities, I want to turn the question over to you. We've journeyed through the physics, the philosophy, and the profound implications of it all, but this isn't a conversation that ends when the video does. The most fascinating perspectives often come from the community of curious minds just like you. So here's a thought to sit with, a question I'd love to hear your personal take on. Given everything we've explored, the breathtaking fine-tuning of our universe's constants, the staggering mathematical odds, and the mind-bending theories trying to explain it all, where does your intuition land? Do you find yourself leaning toward the idea that we are the beneficiaries of unimaginable luck, a single rare universe that somehow beat the cosmic odds entirely on its own? Or does the evidence point your mind toward something grander, making the concept of a vast, generative multiverse, constantly spawning new realities, feel like the more compelling answer? Perhaps your conclusion lies somewhere else entirely, in a synthesis of these ideas or a different interpretation we haven't even covered. There are no wrong answers here, only different ways of marveling at the same incredible mystery. I am genuinely so curious to know what you think. Drop your thoughts in the comments below and let's get a real discussion going. Share your reasoning, your doubts, or even what you hope might be true. Let's see what kind of fascinating conversation we can build together, right here. Trying to picture the sheer scale and strangeness of these theories can feel utterly impossible, but there are some wonderfully creative ways to wrap our minds around these cosmic concepts. Think of it like trying to describe the ocean to someone who has never seen water. We need the right metaphors and visual tools to make the unimaginable feel just a little bit more tangible. One of the most effective ways to visualize the inflationary multiverse is with that classic image of a rising loaf of raisin bread, but let's push that analogy even further. Imagine not just one loaf, but an infinite bakery where the ovens never turn off. Each individual raisin is an entire observable universe, complete with its own billions of galaxies. Now the dough between the raisins is expanding at an incredible rate, pushing each universe further apart, ensuring they never meet. But here's the crucial part: new dough is constantly forming, and with it, new raisins, new universes are always bubbling into existence. Our entire cosmic history, from the Big Bang to the distant future, is all contained within our single, tiny raisin. This animation helps us see that what we call the universe is just our local neighborhood in a sprawling, ever-growing metropolis of realities. For the quantum many worlds interpretation, we need a completely different kind of visualization, one that captures the idea of constant branching. picture a single glowing line representing the timeline of our universe. Now imagine that at every single moment where a quantum event occurs, like the decay of a radioactive atom or the path of an electron, the line doesn't just move forward. It splits into two or more new parallel lines. Each new line represents a universe where one of the possible outcomes became real. Now speed this process up. Not just once, but trillions of times per second at every location across the cosmos. The animation would quickly explode into a shimmering, fractal-like tree of possibilities, with every branch representing a unique reality where history unfolded differently. It's not a tree with a few major forks, but a near-infinite, impossibly dense thicket of branching paths, where every conceivable outcome is realized somewhere. This helps us understand that the you in this moment is just one version of a near-infinite number of selves, each living out a different variation of your life story. The most difficult concept to visualize is undoubtedly the brane multiverse from string theory, because it requires us to think in higher dimensions. A helpful, though imperfect, thought experiment is to imagine our entire universe as a single, two-dimensional painting on a vast, stretched canvas. We, as beings living within that painting, can only move left, right, up, or down. We have no concept of the third dimension that exists outside our flat world. Now imagine another painting, another entire universe on a separate canvas, floating just a millimeter away from ours in that third dimension. To us, it's completely invisible and unreachable, even though it's right next to us. These canvases are the branes, and the higher dimensional space they float in is the bulk. A simulation could show these vast, flat sheets floating and sometimes rippling in this higher dimensional space, and if two of them were to collide, it could create a violent, energetic event, a big bang giving birth to a new universe right on the surface of that brane. This visualization, while limited, gives us a glimpse into how entirely separate realities could be physically adjacent to us yet forever beyond our perception. Ultimately, the goal of these visualizations isn't to provide a perfect picture, because our brains aren't wired to truly comprehend infinity or higher dimensions. Instead, these thought experiments and animations serve as bridges. They are conceptual scaffolding that allows us to climb a little higher in our understanding, to peer just a little further over the horizon of the known. They transform abstract equations and dizzying probabilities into stories and images that we can hold in our minds, even if just for a moment. They remind us that the universe is far stranger, more vast, and more wonderful than our everyday experience could ever suggest, and that the quest to understand it is one of the greatest adventures of the human spirit. Where does that leave us then, after this journey through the cosmos? We've seen how the fundamental forces and constants of our universe are balanced on a razor's edge, set with a precision that defies belief. We've explored the multiverse as a potential solution, a vast, perhaps infinite, landscape of realities where every possible set of physical laws plays out, making our life-permitting existence a statistical inevitability rather than a miracle. And we've considered the alternative, that this breathtaking fine-tuning might be evidence of a deeper design, a cosmos with intention woven into its very fabric. The truth is, the mystery remains wide open. Modern science has given us the questions, but not the final answers. It has provided us with a map that points toward incredible, mind-expanding territories, but the terrain itself is still shrouded in wonder. This isn't a failure of science, it's its greatest triumph. It means we are living in a time of profound discovery on the very frontier of understanding. The conversation between coincidence and design is not a debate with a winner and a loser. It is a dialogue that pushes our species to think deeper, to question more fundamentally, and to look at the night sky not just as a collection of stars, but as a question written in light. So as we conclude, I encourage you to carry this sense of awe with you. Let it color the way you see the world. The next time you feel the warmth of the sun or gaze at the depth of a starry night, remember that you are a part of this incredible cosmic story, a conscious being in a universe that seems perfectly arranged to allow you to exist and to wonder why. Your curiosity is the latest chapter in that story. Keep asking these big questions, read, explore, and never stop being amazed by the profound mystery of it all. If these deep dives into the fabric of reality fascinate you, you're in the right place. We're committed to exploring the most futuristic and mind-bending topics, from the edges of cosmology to the frontiers of technology. Make sure to subscribe and hit the bell so you don't miss our next journey into the unknown. The universe is full of secrets waiting to be uncovered, and we can't wait to explore them with you.